Okay, so Sedstrat, as we used to semi-lovingly call it back in school, sedimentation and stratigraphy. This belongs in a conversation about sedimentary rocks. You could study other types of rocks when you think about stratigraphy, but it's easiest and best introduced in this context. We mentioned probably in passing at some point, strata means layers. Okay, graphy is a loose translation of studying and writing about and so on and so forth. Some bad Latin English there, but the study of layers and sedimentary structures are things that we find within the layers of sedimentary rocks. Speaking of which, what type of rocks are we probably looking at there? Sedimentary rocks. Yeah, you see the layers, right? We know that there's a type of metamorphic rock, of course, that shows layering. We call that gneiss. But otherwise, when you see layers, you should probably think of sedimentary rocks because they're deposited, as we learned, little by little, layer by layer, just like dust accumulates on your shelves at home. So as you can imagine, to get a set of rocks, that high, there's a scale bar there, so maybe it's not that high, but you could imagine it takes a good amount of time. To acquire a set of sedimentary rocks, if you could imagine the Grand Canyon for a moment, you can imagine that requires quite a bit of time, let alone for that river to cut back down through it all is a whole another set of time. So we talk about time a lot when we talk about sedimentation and stratigraphy because it is really all we have as a record of history from before people were around to take notes. So this can be, if you dig it, this can be really, really neat stuff. So we're looking at these rocks here, and it looks like, Utah or Nevada, some deserty place, could be Africa maybe. That's Mars. Okay? So everything you've learned about sedimentary rocks to this point is true, and don't really see any other sort of way that sedimentary rocks can form. So when we see them on other planets, we have to assume that the same processes that occurred on Earth to create them occurred there as well. So if you're wondering, why, isn't that an amazing image, by the way, for another freaking planet?
That is cool.
I get the feeds because I read a lot of articles about this stuff, but there's a Mars rover post that comes through on Facebook. I'm sure it's other places. I know your generation doesn't really do Facebook, but once they take the time to patch everything together, you get these three, how you hold your phone up and you walk like around this way and move your phone around in circles, panorama kind of stuff. They've got these amazing panoramas from Mars that the rover has sent down, and the image quality is just mind-boggling. So yeah, no more of these fuzzy images, that you probably grew up with, that I definitely grew up with, from other planets. We've got high-def crap up there, man. It's amazing. And that's how we're finally able to do some decent research, okay, let alone, the samples and whatever that we've gotten at this point from various places.
So do we know what happened on Mars to make all the water, disappear?
Yeah, there's a handful of thoughts, and it's unfortunately not in the purvey of today's lecture to get a chat about it. I'd love to, but mainly there's a handful of issues going on there, mostly revolving around its much thinner atmosphere, much lower gravity. They're kind of interconnected there. It went through all the motions we did, just a lot faster. They also feel that tectonics is no longer happening there, so there's no longer, I don't see no heat coming from the inside of it, but very little. So it's not a dead planet. There is still ice. It's at the poles, and it is ice, because sometimes you talk about these weird planets, Saturn and stuff like that, and they'll say ice, and they just mean frozen gas of God knows what. But no, like ice, like we know it, is there. So it's, there is still water there. It's just so dang cold. The what exists, and there might be some in the ground. So the paleontologist in me really gets excited, and the government skeptic or whatever you want to call it, you know there's some damn fossils in there. There gotta be. I would love to see. I'm sure a million people would love to see them. But whether or not they evolved, had the opportunity to evolve as far as we did before things went to hell is another question. But there's got to at least be some stuff on the lower evolutionary ladder rungs. But anyhow, again, not the point of today. Not the point of today. Really cool stuff, but not the point of today. So sedimentary rocks, the layers, okay? What's the only new thing here? The only new thing here is beds or bedding, okay? I hardly ever say bedding planes. I'll say bedding, but the planes, a plane is a flat surface, so that's what the plane part is there for. Should be, as we mentioned the other day, horizontal, flat, like your notebook, like your textbook, like a deck of cards. All right. We also know that there are things that can change that. All right. If you looked out your car window at all when you were riding around the planet with your folks growing up, you probably noticed that not everything out there was flat layers. Now, what you attributed that to and at what point in its history is another question entirely, but you know that there's wavy, warped stuff out there, slanted stuff, straight up and down stuff. All right. If they're sedimentary rocks, they were not made that way. Something happened. So anyhow, just sedimentary rocks, sediments are deposited in layers, therefore sedimentary rocks are layered. Can you see the layers all the time? No. Think about those sandstones we saw in lab. All right. The grain size is so uniform, so this, so that, it just looks uniform. But they were still put there little by little by little. Think about if you've been lucky enough to spend any time at the beach, the sand blows around back and forth. Okay, and every time it blows this way, it puts a new layer of sand over there, or removes a layer of sand from where you were just at. So, layers. Towards the bottom, it blurs out because we've got what they call scree slopes there. Don't really worry about that. It's just all the rubble and refuse at the bottom of a cliff. All right. So if you're wondering why it kind of blends out there, it's weathering, it's smooth. But then you do actually see the bands pick up a little bit closer towards the bottom there. So in some areas, that's kind of neat. When you're really lucky, it is separated out by colors. Not all rocks are the same color, as you guys have been learning, right? Excuse me. Just another example of what beds or layers look like. We'll talk more about this in a bit. All right, superposition. We've mentioned some of these words in passing. Now you're formally getting them. If you haven't in a previous thing already. We talked about geologic time this semester. I don't always do that. So depending on the semester I'm using this recording over again, this is more for the folks at home. We may not have talked about it. So in an unaltered section of rocks, the oldest rocks are on the bottom, the youngest rocks are on the top. All right, and most of you smiled and nodded at me the other day If you're still not on board with that, think of your mail, all right? You probably have a place in your home, your wherever, where you guys put the mail. Every day you walk in, you throw the mail in a pile. You pull out what's important, you leave everything else there. Junk mail, as we used to call it. All right, now say it is the end of the week, and you remember that some pizza coupons came earlier in the week. Where are you going to look for those coupons? In the top of the pile or the bottom of the pile? Bottom of the pile. How come?
Because that's where the first mail was placed.
That's right. It's just they've been there longer. It's where the older mail would be placed, and it's the same exact no reason that for sedimentary rocks. Okay, because the sediment has to pile up time over time. The stuff that's on the bottom has just been there longer. Now, what happens if your dog jumps up on the table, knocks the pile over, somebody actually bothers to pick it up, sets it back on there? Now where are those pizza coupons?
Who knows?
Who knows? Exactly. Same thing happens in Mother Nature, except it's not dogs.
Well, we don't know. It could be a giant dog.
It could be. Could be a giant dog. That'd be cool. But we've got earthquakes, we've got plate tectonics, we've got stuff like that can mess up the layers. Doesn't usually reshuffle it like a deck of cards, okay? But you will certainly get instances where, due to some serious moving around, a section of rocks that's way older gets thrown up on top of a section of rocks that's younger. Right? Usually there's clues that help the folks in charge of that sort it out. But generally speaking, and that's what that unaltered is about, okay? As they were made, as they were deposited, this works. So we can expect the rocks on the bottom to be older than the rocks on the top in this here image. Original horizontality in an aquatic environment. All right, that there is a special situation here. Sediments are deposited in horizontal layers. Now, I've been talking about this like it's just a general rule, and I want you to remember it as such. But technically speaking, okay, this basically applies to an aquatic environment. That's where the majority of your sedimentary rocks are going to be from anyhow. But there are certainly desert deposits and so on and so forth, beach deposits. And the idea is, I don't think I have a drawing of it here. No, I don't. But if you can't picture it, draw it on your notes there. Your typical sort of bowl-shaped lake, right? And all we're really saying here is that the sediments aren't going to mirror the bottom of that lake bed, the bottom of that bowl. They're going to actually roll down the hill and pile up along the bottom and still make those straight layers. So you don't get deposition along the side. Gravity works even underwater. So you'll get your basin deposits still in flat layers. And like I said, I argue about this on land as well. You've got, good enough reason for things to keep rolling downhill on land too. But yeah, question? No? Oh, I thought you had a question. Yeah. This is actually my picture. I'm starting to wonder if some of the other ones were.
That one is like slanted as well.
It is. I'm standing up straight. I promise you that, or at least as straight as I can be after the hike out there. Yeah. So exactly. That is probably better for original horizontality than superposition. So that's probably why it's here. But yeah, that's a bit of a slope. So something uplifted that. Because you see the stuff in the background, I think that's probably why it's the juxtaposition there. Those are seriously flat. And then this one here, while still layered, it's got a good incline to it. There's a reason when you say you want to study geology that they send you out west. You can actually see the rocks. You don't have all this crazy vegetation here and everything like we have.
Are they, you think a bunch of those rocks are out west because of the plate tectonic stuff?
Mm-mm.
Same reason why the volcanoes are?
No. I mean, we've got them here. You just can't see them. They're just covered with...
I know, but like the reason they're more visible.
It's simply because there's not a big soil base and vegetation out there. Yeah, there's different weather conditions. I mean, there's a couple of things, but I don't necessarily think plate tectonics and volcanoes, no. But yeah, and and of course the weather feeds into the whole vegetation bit as well, so it's all related. Lateral continuity. This is always the hardest one for me to explain. It is, again, really simple, but you guys sometimes just don't get it, and I'm sure it's my fault. Lateral continuity. In an environment, a rock layer, and then I have in parentheses an environment, we'll worry about that in a second, extends out horizontally in all directions until it doesn't. What? Well, if you imagine that a rock layer is a product of an environment. We've been talking about deserts, we've been talking about seashores, we've been talking about lakes. Those are all environments, right? At some point, that lake ends and it starts becoming a field. And that field at some point turns into a forest or a swamp or whatever. You get the idea. You've seen the earth. At one point, it blends into another environment. That environment may not be depositional. It may not make rocks. It may erase rocks. It might be erosional. So what we're saying here is that rock layers, rock beds are finite. Okay? And again, something that you know, and almost by telling you guys at this, especially at this level, it almost confuses you more than not, because of course you would assume that the rock layer ends. And at some point there might be more rocks, or there might not be more rocks. Again, you've been walking around the planet for 20 years or so now. That's all this is saying, okay? But it's tying it back to the idea that these are functions of an environment. Environments change, the rocks change with it. Sure that, yeah. That's an arch out in Utah. That's me underneath there. Somebody's very far away. That's Arches National Park. And I'm not entirely sure why I put this under or after lateral continuity. But again, sort of the same idea is that, again, we could look at the rocks here in the foreground and look at the rocks in the background. And if they look the same, they have the same colors, the same striping, so on and so forth, we could assume that they're the same rocks in the same environment. All right, we mentioned this the other day as well this semester, so a lot of this is kind of new, which is nice for you guys. I mean kind of review, not new, but not always every semester. So we talked about cross-cutting relationships. The disrupted pattern is older than the disruption. What? Well, think of igneous intrusion cutting through a layer of bedrock. The layer of bedrock had to be there for the intrusion to be able to cut through it. The intrusion is younger than the bedrock. While sedimentary rocks are annoying to date, we told you that igneous rocks are pretty great. So you could date that intrusion and get an idea, at the very least, that those rocks are older than said intrusion. See how we mix relative time and absolute time together here a lot. Principle of inclusions. Again, this is primarily for sedimentary rocks. All right. The rock is younger than all the stuff that makes it up. Kind of makes sense, right? What is younger, the bologna or all the animals that went into the bologna? The bologna, or what is older, all the animals. All right. So inclusions, cross-cutting relationships, same idea, different scenarios. Uniformitarianism. We actually started this conversation by talking about uniformitarianism, but without the vocabulary word. When we talked about what makes sedimentary rocks here, can also make sedimentary rocks on Mars. Usually, and in the past, we've only ever been able to apply uniformitarianism to the Earth because we couldn't directly study other places. But now that we can, it's a really great tool. And I am kind of gliding through these because we did, again, discuss these the other day. Okay, new stuff. So you remember those pictures we showed you a little while ago? You might have saw a red rock, a slightly less red rock, maybe a black rock, and then a white rock. And then I went back and did red rock and this, that, and the other again. We group rocks together, especially if you see that pattern repeating. Okay? Not always, doesn't have to repeat, but if they're related, if they relate to an environmental sequence, if they have any meaning that the person studying it can tie them all together, they lump them together in something called a formation. Okay? And sometimes it's just one rock type, sometimes it's, like I said, this repeated pattern. And the names are pretty straightforward. Location and rock type, if it's one type of rock. They're not going to say the Utica, shale, sandstone, and limestone. No, they only say the Utica shale. And the Utica shale is actually a very important shale. I was very surprised, and I've been teaching this my entire life, but very surprised to find out that, it actually goes into Ohio. And that's what they were tapping back in the fracking days. And you might say, well, why didn't they call it the Ohio shale then? Well, because it sticks out over here. This is where they found it. And so the guy, typically a guy, at least in the past, that found it, got to name it, said, oh, this is a famous shale. This is an important shale, I should say, not famous, in Utica. And guess what kind of rock it is? It's a shale. Now, if it's a repeated pattern, shale, limestone, shale, limestone, shale, limestone, which is very common, they usually use the word formation. Still have the name. Where is it best shown? Where was it first shown? So the Albany Formation is another great example. I forget exactly what rocks are included in the Albany Formation. It'd be a good guess, though, that it is shale and limestone. There's a lot of that around here. Shale, as you guys know, comes from mud. Limestone comes from offshore marine. When sea level goes back and forth, which it has done a gajillion times over history, that one spot on the planet goes from underwater to near shore, to underwater, to near shore, to underwater, to near shore, back and forth and back and forth. All right? So when you stand there and look at its history records, it's like paging through a photo album. You see that this was shallow water, it was deep water, shallow water, deep water, shallow water, as you go through the shale, limestone, shale, limestone, shale, limestone. All right? Somebody studied it, decided that they were all related. They're going to group these rocks together. Where am I studying them at? I'm in Albany. Okay, this is the Albany Formation. So if you see a rock type, there's probably only the one rock there that's important. If you see the word formation, there's a bunch of rocks, or at least a couple. All right, an example. We got the Kaibab limestone up on top, then the Torreweep Formation, then the Coconino Sandstone. What kind of rock is in the Kaibab limestone? It's not a trick question, folks. There you go. All right, geologists are nothing if not tricky. Not tricky. How about the Torreweep Formation? We don't know. But, well, here's the thing. You got limestone on top, sandstone on the bottom. Both is a great thought. Okay. It could be a period of time where, the sea level or whatever was going on here went back and forth, back and forth, back and forth. Sandstone, let's just say that we'll genericize it here. We'll stereotype. We'll say that was a beach. So for a very long time, there was beach there. And offshore was either, that way to the right of the screen or to the left of the screen. Who knows? Out of context like this. Torreweep Formation, we see maybe a transitioning period happening. Sea level rose or shrank. Again, we're out of context here. But if we're transitioning into limestone, it's a good guess that the water's getting deeper. Where do you find the best example of the Coconino Sandstone? Wherever Coconino is. Okay? They use these names for that reason. Now, there's one last word on here, contact. Contact is simply the place where it transitions. Okay? It's the boundary, if you would. And they don't have nice black lines like that, unfortunately, or even dashed lines. Sometimes it's really subtle, sometimes it's incredibly obvious. You switch from a black rock to any other color rock, okay? You're going to notice the change. What's much more subtle is what a contact can imply. All right? It could, as I just said, be a boundary between two different formations, but remember how I introduced it. It's a change in the environment, right? Not all environments make rocks. Some environments erase rocks. So what a contact could also represent is a huge gap in time. We call that then an unconformity. An unconformity is a special kind of contact that represents a gap in time. I'm going to assume that most of you have driven by the Little Falls exit in your time around here growing up, if you're from here. All the big shale, it's what's on the cover of your lab book, right? So let's just say that Bill Nye and Al Gore and all those guys are absolutely right, and sea level's going to rise, and not just were they right, they were so wrong in how quick and how deep it's going to happen, and we actually end up under sea level again. Not going to happen anytime soon, but it will eventually. You're going to then get some shales, some limestone, some whatnot deposited on top of that rock that's existing there. Let's then jump thousands and thousands and thousands of years into the future, and they decide that Route 90 was in a good place for a good reason. So whoever's living on the planet at that point decides to rebuild Route 90, and they cut down through all that rock, and all that black shale is still going to be there, but there's going to be a bunch of new rock on top of it. In between that is a contact, is a gap in time of like 500 million years. All right? If you just don't necessarily go looking for that, you're going to say, oh, wow, we went from shale to all this stuff, and wow, that must have been a really neat environment. This is why using absolute dating techniques and so on and so forth is important. You can't tell this stuff just by glancing at it. So that was one thing that they did potentially miss, going way back when, 18-something, when they were naming all these rocks and all that stuff. We couldn't really test. Sometimes you could, they were able to sort it out, but a lot of times not so much. So an unconformity, at any rate, strictly put, is a contact that represents a gap in time. Could have been an erosional period. I don't know if I have another slide on this or not. Yeah, so could have been a period of weathering and erosion, or simply a period of no deposition. Again, not all environments make rocks. But a gap in the rock record is a gap in time, no matter what. So, if I haven't said it enough, like 17 times already, rocks equal time. While they were accumulating, life was going on around them, in them, through them. And again, it takes time for those to build up, for those to wear away, for more rocks to build up on top of those. Okay? Rocks equal time. And again, we're talking about sedimentary, but this applies to igneous and metamorphic as well. Igneous is tough because unless it's lava at the surface, it could take a very long time to cool, to turn into rock, depending on whether it's close to the surface or deep down inside the earth. Metamorphism. Yeah, metamorphic rocks previously were rocks, and then we changed them to new rocks. Well, how long did that take? Good question. You could tell, but we saved all that hard stuff for later. We talk about the easy rocks right now, sedimentary. Easy to visualize. Hardly ever confusing us. Okay, on the rock cycle lecture, you saw the little dots, the little dashes, the little bricks. Remember those? All right. And again, those are, well, I don't want to say universal, but they are global. It's a way of overcoming language barriers. It's a way really easily of looking at a map and knowing what you're seeing. And you're going to see these again and again. I'm not sure this semester whether or not we're going to get to talking about groundwater and such. Time has kind of gotten away from us here. But you see these symbols again and again when we talk about groundwater, because you want to know what kind of rock your aquifer is coming from, where your groundwater is coming from, and so on and so forth. So this is the sequence then. We see limestone on the bottom, followed by shale, followed by sandstone. Somebody remind me, where did I tell you limestone forms? Water. Near shore or kind of offshore, pretty kind of far of it? Somebody help her out.
Say that one more.
Limestone. Kind of far offshore or kind of near shore?
Near.
Okay. Yeah, I might not have stressed that enough. Limestone is deeper water. Okay? Limestone is deeper water. Shale is the muds close to shore. How about sand? Where do we find sand? Yeah, the beach. Okay. So you literally have a progression. You guys don't get to walk it. Okay, you're not going to walk from sand to mud. You'd be underwater. But it is there. It is there. With weathering and erosion, we talked a little bit about sorting. Okay? And the way this stuff gets sorted is by grain size. So what's behind the sand, what's behind the beach? Well, nowadays it's parking lot. But the funny thing is at least if it's gravel, it still follows nature, right? Because you've got your pebbles and your cobbles and whatnot in the parking lot for your gravel. Then we go to sand. Then we go to silts and clays to make the muds. Anywho, limestone forms even further out. So if this were one section of rock at one place, you're standing in front of it next to a road, out in the woods, wherever, you know that this environment was under not just water, but salt water, a marine environment. Limestone only forms in marine environments. So you know that over time, it was deep water, then it got shallower water, and then it was beach, all right where you're standing. So if you could rewind and somehow visualize, I'm sure they've done this in a movie, rewind and somehow visualize that environment through you, where you're standing there, right there, through the past, you would see all those environmental changes. And we know that just by looking at the rocks there. Of course, what I just talked about has vocabulary words. Transgression and regression. We might not know what transgression means at this moment, but what does regression mean? Go back, all right? So transgression means coming up to. I think each of these has a slide, so don't worry. But, so transgression, we're talking about the shoreline, okay? The water level. So transgression means sea level is going to rise. Regression means sea level is lowering. And see, I was raised for the last, not raised, trained, taught, whatever word you want, for the last, well, I've been teaching going on 25 years, and then my training, education before that. I've been taught that this is normal, this is a given This is how we get the rocks we get. So when we hear these people on the radio and on the news and wherever talking about whether or not sea level is rising, and of course it does. Of course it does. And they're not stupid. They were freshmen. They had to take geology class as well. Okay? These people don't not believe in it. They're just not allowed to say that they understand it because their constituents, etc., the people who put money into their campaigns, don't want to think about it either. Nobody is that stupid that they don't believe this stuff isn't happening. They just can't afford to say it out loud. So it is. It's like saying plate. I don't believe in plate tectonics. Why? Have you not seen earthquakes? Have you not noticed, mountains being built and so on and so forth? And now that we have satellites, I mean, we can literally tell you how fast each continent is moving and in what direction.
That's not plate tectonics. It's the giant dogs.
Yeah, it could be those dogs again. Or the giant turtle that we're riding on. And
Godzilla. And then there's elephants under that turtle.
Yes,
or something
sir.
like that.
Yes, they're on top of the turtle.
Oh, yeah, that's right.
They got to stand on its shell. So, at any rate, lest I digress. So, trying to figure out what I'm looking at here, because that sure looks like I've got. Oh, that's okay. So that first one is sand. I thought the one in the middle looked like dots to me, my poor eyes from this site. The one in the middle is supposed to be the shale. So again, we're seeing sand, shale, limestone. And this is what I've been telling you for the last couple minutes. If you were super tall or if you had a scuba suit on, you could walk out to where the sand turns to mud. But a easier example, this happens to some extent, although it's imitation. If you've ever gone swimming in a lake, all right, we go through great means to make sure that the shoreline of the lake is at least, if not rocky, kind of sandy, because nobody wants to just like step right into mud, right? They wouldn't go in your lake. So we put something there. And then if you go out far enough, you do get into that muck. And again, you may or may not have experienced this. Again, that's probably artificial, but it's the same idea here where you start on the sand and you go out to the mudstone. Now what you're not seeing is that underneath that limestone, yeah, there's probably shale there. Because again, time. So what we see happening then is if we want to stack that shale, the one in the middle, let's say we have to move that to the left. All right, this is an application level question here, kids. This is something you should be able to do at this point. To move the shale to the left, what do we have to do? Increase sea level or decrease sea level?
Increase.
Increase. All agree? Show of hands. Disagree? Show of hands. Not sure what the hell we're talking about? Show of hands. Okay, so a few hands went up there. So this is because of, we'll just say, arguably water depth. Okay? Sand is in one place, shale's a little farther out, limestone is a little further out than that. If you want to create a exposed layer of rock that you can see sometime in the future, and we want to move the shale, stack it up on top of the sandstone. We want to move the shale over one notch to the left. It would go on top of the sandstone at this point. What do you have to do in the environment to achieve that? Raise sea level or lower sea level? So it's a function of water deepness. So you have to actually raise sea level. So sand would get deposited off screen. And the shale gets deposited where the sand is currently being deposited. The limestone would also move up a notch as well. You get limestone on top of the shale. Which is why when you're driving on 90, you see every so often those cream layers in the black shale. limestone. All right, it represents a time when water level got deeper. You put limestone on top of shale, all right, that means that in that same exact spot, it's now, for that time period, it's now deeper than it was. So we want to have a transgression, all right? If we find shale on top of that limestone, well, that represents a regression. We're moving the deposition to the right, we're moving the shoreline. Maybe that would have been an easier way to say it. Which way do we need to move the shoreline? So sea level is lower, the shoreline is farther out. Or sea level is higher, the shoreline moves to the parking lot. Because that's what we put next to all of our shorelines now. I totally see the point of having parking lots near the beach. I'm fat, I'm lazy, I don't like to walk very far. But we do try, at least when our family goes out, to try and find some natural places still out there. And there are plenty, state parks, national shorelines. I encourage you, if you are lucky enough to get to the beach sometime, leave the boardwalk area, leave the manicured beaches, and look for a state park that's on the shore. You'll see a lot of what we're talking about. All right, we are segueing, but we have plenty of time. Good. We're now segueing. We're leaving the philosophical kind of stuff, if you would, and just getting into some matter-of-fact kind of stuff. We're now talking about sedimentary structures. So these are the doodads and implications left behind in between those layers that we've been talking about. These are the lost handkerchief at the scene of a crime. These are the fingerprints that show up on a doorknob. These are these cool little tips and clues that help us more than just dating a rock and looking at a grain size and guessing what environment it came from. You find sand grains with seashells in it, you're going to guess one thing. You find sand grain that doesn't have seashells in it, maybe has a coyote bone in it, you're going to guess it's a different thing. That's what sedimentary structures do. This last bullet sounds kind of funky here, but it's really straightforward. Formed after deposition, but before lithification. In other words, the sand or mud or whatever had to be there, or we wouldn't have been able to make that fingerprint in it. But it formed before lithification, which means before it turned to a rock. Kind of hard to leave a footprint in a rock. You could, I suppose, but. So again, kind of a well duh, but had to be said. And in all honesty, apparently way back when we were just starting this stuff out, we're going back to like Greeks and Romans and all that stuff, I think Greeks. One of the many ideas about fossils was that the organisms somehow crawled into the rocks and died and got stuck there and died. Okay? They didn't know what to make of it. So, the fact that we're saying before it turned into a rock is actually there for a reason. All right. What are we looking at here? What are some options, some possibilities?
Bigfoot.
Okay, a foot. Did you say a beak?
I said Bigfoot, like big.
Bigfoot. All right. Not the Bigfoot, but a Bigfoot. Is it the foot itself? Are you saying?
Nope, it's just the print left by
A print. Okay. What else might it be? I'm not necessarily agreeing or disagreeing with him, but just looking at it, what else could it be? Look like anything else on the planet? Kind of looks like a plant. Yeah. All right. So let's go back and assume that you guys don't necessarily know everything that you know at this point in life. That's something else that we have to look at with science. You guys at 20 some odd years of life know way more about stuff let me rephrase that. Know way more stuff than some 20-year-old 100 years ago. And they knew way more stuff than a 20-year-old 100 years before that. You have an accumulated body of knowledge that that grows as civilization goes forward. Now, might that person 100 years ago know way more about farming than you do? Sure. Okay. So most of you aren't farmers, but you might be. So we're not talking about that necessarily, but just literal volume of knowledge that a person can have. And criminy, you guys with the freaking internet in your pocket, your generation, I think we're seeing exponential growth here. At least those who finally use it for powers of good. All right, so my point being, give me an argument or two why this is probably a footprint and probably not a leaf. But I was definitely fishing for the word leaf there. Thank you. Yeah, it's deeper, okay?
A lot thicker than that.
You have to be a hell of a leaf to leave an impression like that, right? And not only that, there's another indicator there that's a lot more subtle.
No leaf veins.
Good point. Good point. We don't see the little veins in the leaf. Yeah, those could be. I've seen pointy leaves, though. I've seen pointy leaves. But yeah, that's a great example. I'm looking at the heel impression. All right. Most leaves don't have a giant ball at the bottom, but there could be one out there. Could be one out there as well. And it could be a prehistoric leaf that we don't even know exists. But we had it basically on deck, right? It would be a really heavy leaf to leave an impression like that. So, okay, yeah, it's a footprint. All right. And where do we go from there? Well, okay, what has 3 toes? Maybe a bird. I don't know. Certainly doesn't look like a mammal. You could spiral out from there. So, what this is, as you see, is trace fossil, or the proper terminology, ichnofossil. All right, which is like kinda. It is not the organism itself. It is evidence that the organism was there. That's what a trace fossil is. It's leaving a trace, if you would. All right. So that is not the dinosaur. That's not even the dinosaur's foot, but it is a footprint. It tells us there was a dinosaur there. And that, my friends, is what we pretty much have in New York State. We don't got a whole lot of dinosaur bones at all. But we got a bunch of footprints. Mostly to the east, over by the Connecticut River and whatnot, over that a ways. There's some further down by Jersey. But we haven't found any bones yet. Again, likely it's the environment. They're mostly in stream sort of areas. So the bones were beaten up, broken, shattered, at the very least floated down to one of the bays. But the footprints, if they get covered up quick enough by sediment, they get to stay. So it doesn't have to be a footprint. It could be something is burrows. Okay, believe it or not, burrows are really amazing. Picture Pac-Man, if you would. The maze. The place I went to grab my zebra toes so I could study them in grad school. I told you that on day one, right? I studied zebra toes. It's kind of weird. We went out to Nebraska, Broadwater Formation in Nebraska. It was a huge picture, kind of like an African savanna environment right now. That's what Nebraska looked like back then. And one of the things they had on the wall at the museum was a huge cutting, about the size of the wall in this room. And it was a flooded, I forget if it was gophers or what it was, but this whole system of burrows. And it was in whatever kind of sediment it was in, but the flood mud was a different color, so you could see it just filled all the poor little, drain the critters right out of there. This was before cell phones. Well, I had a bag phone, which didn't have a camera on it. I wish I had pictures. So, because I can't remember if there were fossils in there. I think they probably would have shot right out like a bad comedy movie or something. But there might be some fossils in there. So tracks and trails, footprints. Footprints are the most common. Another really cool ichnofossil is something you've all, again, if you've had an opportunity to get to the beach, freshwater or salt, you may have seen. If you've ever seen a tiny little hole, perfect little drilled hole on the back of a seashell, that is caused by a snail. I'll never forget, I was at a conference years ago, and I was walking around. I didn't feel like looking through the 90-page booklet, so I was just wandering the halls looking for something that sounded interesting. And I saw predatory snails of the Cretaceous. I'm like, predatory snails? Okay. You know, I picture cougars and, stuff like that, not snails attacking things. So it turns out there's like pretty much one thing that's slower than a snail, and that's a clam. And snails are vicious. If you've never had an opportunity to look at a snail, some people have in their fish tanks, but most don't look at snails. Their mouth is really bizarre. They have a sort of a suckery kind of mouth, but inside of that is what they call a rasper. Have you ever seen anyone drill a doorknob hole? Right, it's a special bit you put on a drill that goes woo and spins basically that hollow core right out of it. Well, that's what snails have in their mouths. So they climb up on the back of a clam, they do their little doorknob hole driller, rasper thing, and they slurp out the yummy ingredients inside. So that is a trace fossil. It's not the fact that the snail, it's not the snail, it's the fact that the snail was there. All right. Gnaw marks on a bone, same idea, bite marks. Shows that there was a predator in the environment. So, lots of neat things with trace fossils. What might that trace fossil tell us?
There was a tire there.
Yeah.
Or some horrific scientific abomination of replacing animals' legs with a single tire.
Okay, yeah, that might be a little bit out there. You might lose your funding. But, yeah, so we're making trace fossils nowadays. Will this one be there in the future? Probably not. It's in a parking lot next to a curb. I had one that was a footprint. I don't know what happened to that one. But, so tire tracks. We're still making them. Oh, there's this. I found one. Okay, cool. I forgot I found this picture. Snail marks.
Snark.
Oh, really? This is a video?
I can barely tell where the snail.
All right. Well, apparently it's a video. We got to watch this.
I can barely tell where the snail snarks.
Snail snarks. Moon snail preys on cockles. Folks at home, if this isn't coming through for you, please let me know and we'll get you the link. Not sure why it's not playing. Oh, you're not seeing it. Hold on. Hold on. Folks on campus aren't seeing it.
Cockles are abundant. They attract the attention of a more aggressive mollusk. The moon snail can inflate its foot to 4 times the size of its entire shell. A foot that serves as both a burrowing tool and a predatory weapon. The cockle, however, has a few tricks of its own. Its foot is a powerful digger, but it can also kick away forcefully when danger approaches. If the moon snail loses its hold, it can also burrow down and surprise a buried cockle.
Predatory snails, folks. You see it here first.
This time, the aggressor succeeds. The moon snail's enormous foot begins to smother the hapless cockle. Even a hard shell can't stop the well-equipped moon snail, which can drill right through to feed on the animal within.
So see, I'm not nuts. Okay, what's that? A fossil. Good, we could read. Fossil of what?
Some sort of fish.
Some sort of fish, yeah. All right. How do we know it's a fish?
It looks like a fish.
Fair enough. Got fishy parts, right? Okay. So we see some fins there, or more so, we see the bones where the fins used to be. You could even see some lips and an eye, right? And some gills.
I think so.
Yeah. Yeah, so, yeah, a fossil is the preserved remains of the organism, just as a definition, okay? Unlike the trace fossil, which was evidence of the organism. This is the, for lack of a better word, the actual organism, actual in quotes, okay? Because it's usually there's, and this is a whole other chapter, so I don't want to get too far, but the material is replaced or there's an imprint of it. You guys know enough about fossils from being kids to really get you through this slide. But typically it is not the organism itself. There are a few instances. Okay, we pull a woolly mammoth out of a frozen soil and stuff like that. Yeah, tar pits. Yeah, you do have this. You have the actual organism caught in some amber. You got the actual organism. But most of the fossils are imprints, fill-ins like Jello molds. Okay, or the material is swapped out. The bone becomes hardened over time, so on and so forth. So, fish are generally speaking good to eat, right? And to things like bacteria and whatnot, they don't really even have taste buds. They just want food. So, if this fish died and stayed there for any amount of time, he would have been eaten, or at least started to decay. And we see absolutely no decay on this fish. Right? All those fins are even in place. Heck, again, we could even see semblances of lips and eyeballs. Not to be gross, but those are the yummy bits. Those go first. The soft parts, okay? What that tells us is actually something important, that this fish just didn't die and fall to the bottom of the ocean or the lake or whatever. He died and got buried super quick, possibly all in one event. So they start to look for, evidence of, well, was this a mudslide? This is sandstone, so not a mudslide exactly, but you get the idea. So there is a whole science in looking at, I don't think I have a slide for this. It's called taphonomy. No, I don't. That studies what happens to the organism between death and fossilization. All right.
Isn't there a super famous fossil of some sort of raptor and another dinosaur, like mid-fight, and then the fossil has them like frozen, like raptors got?
It's possible. I know of some arrangements that way, but I don't know that they were formed that way. The Natural History Museum in Manhattan has in their front lobby. It's amazing because they're the one with the Barosaurus, which is just as big as this building. One of the four-legged guys, big four-legged, long neck, long tail, you know the types. Fighting a, I'll just call it a T-Rex. It's not. It's like an Allosaurus, but everyone knows what a T-Rex looks like. And then there's a smaller long neck. So it's defending its baby against this meat eater. But as far as found as a fossil, I'm not going to say no. I'm just not familiar with it. But we've certainly found fossils with remains in their stomach. That's where you hear a lot about that some of these species were cannibalistic and whatnot, because they find versions of smaller ones of themselves in between their rib cages and whatnot. So where their stomach would have been, so to speak. So fossils are not as simple as just fossils, okay? I won't belabor the point, but as I said, there is that huge study, a huge area of field that studies what happens to them between death and fossilization. And again, implications of environment, right? This probably wasn't a desert. It's sand, but probably not a desert, because why? Well, we found a fish fossil, all right? And more so a fish fossil without bite marks and so on and so forth on it. So we find little doodads that just help us solve these mysteries of what these rocks were. A little more mundane now. This is mud cracks. You see mud cracks all over. When you're around here, between the grass and the curb, okay? You see them at construction sites. You see them near lakes. You see them all around. And really what it shows us is an area that got repeatedly wet and dry and wet and dry and wet and dry. And that it has a fairly high silt and clay concentration. Or we wouldn't call it mud, right? Because mud isn't wet sand. We talked about that a couple times. What happens is that silts and clays are like sponges. They absorb water. And when they absorb that water, they swell up a little bit. When they dry out, they don't necessarily shrink. They try to keep what the previous form that they had, and in order to make that happen, these giant crack marks form. All right. So the mud swells when it's wet, and when it dries, it cracks, but still sort of tries to preserve its swelled nature. Well, that transfers into the rock record as well. You could argue maybe that this is some crazy turtle shell or something like that. But again, if you look more into the context, the environment, stuff around it, it's pretty obvious then that those are indeed mud cracks. You got different grain sizes. You got the mud itself, which is a fine grain, and then it looks like there's a slightly coarser grain that came down, and more than likely this was flooded. Again, so you wet, dry environment. It's not hard to believe that it could, in an event, flood. So washed over it and preserved it instead of erasing it. You've seen that, I'm sure. Okay, same stuff. Just if that could get preserved. I like this one actually because you got two sets of mud cracks there, really. The one in the street there on the top definitely would get destroyed. So he pulls up to the curb, whatever. But there's a chance that some of those cracks got preserved in the grass there. Probably not. Cross-bedding. Your book is going to mention cross-bedding in aquatic or terrestrial environments, aquatic, water, terrestrial, land. I want you to just think of cross-bedding with regards to terrestrial, okay? Just keep it simple right now. So really only the bottom, ignore the bottom picture. We really want to look at the top. And these are sand dunes. I'll show you a picture in a minute of a hardened one. But we talked earlier about sand blowing. If you spend any time out west at all, sometimes the dunes can literally blow over the roads, and they have to clear them like we clear snow out here. Sand is constantly moving and shifting. And if you've ever tried to climb up a hill of sand, you know. All right, that all of a sudden it could just slide and a whole section will come down. Hopefully not with you underneath it. But you might slip and fall a little bit and you laugh if you don't get hurt. It's fun. Sand is constantly moving. All right? And that can be preserved in the rock record as well. You could be walking along and you see this. All right? And again, while you can come up with some, oh my gosh, there were a whole bunch of earthquakes or little faults here and this rock just shifted and shifted and shifted. Or you could go with the most simple solution. I don't know if they still have like a Philosophy 101 class. It's a good class to take if it exists. I think it's Occam's razor is what it was called. Occam's razor, yeah. The simplest solution is probably the right one. Paraphrasing, of course. But so we see the slippage. We see not only that, we see sand dunes represent wind, right? That's what makes a sand dune, blowing the sand. So we can even tell you, prevailing winds. All kind of crazy stuff. So cross bedding, think of deserts and sand dunes. Graded bedding. This is sorting. All right, again, we talk about sorting in weathering and erosion. And we tell you that as a system is slowing down, be it wind or it's easiest to think about water, okay, as a stream slows down, it's going to drop the heaviest stuff first, then the mediumest stuff, and then the finest stuff is last. And if this isn't sounding familiar to you, you need to make sure you listen to the weathering and erosion lecture cast. This semester, class was canceled on that day. We still posted a lecture though, okay? If this doesn't sound familiar, listen to that lecture. And I suppose that's a given during any semester. If I'm saying we talked about this already and you don't remember it, go find that lecture. So what we see here is coarse grained on the bottom, medium grain on top, in the middle, and fine grain on top. Now this also works in still water. If you drop a whole bunch of unsorted sediment into the top, we actually have a lab that we may or may not do this semester. We're running out of time, though, unfortunately. We drop sand down a tube and we time it. Doesn't sound that great, but it's better than staring at rocks, right? This stuff sorts itself out in the column of water on the way down. So the geologist then has to say, okay, well, was this a stream environment? And we're looking at, again, you have transgression and regression with the stream. In the same spot where you have coarse grain, you were getting medium grain, and then you were getting fine grain. All right, that tells us that the stream is moving back uphill. The stream is probably drying up. Or this was a lake environment, and a whole bunch of unsorted sediment was falling into it, and it was just settling out. Heaviest stuff falls first, fastest, then the mediumest stuff, then the finest stuff. So it's called graded bedding. It's graded, it's sorted. Think of a slope, a hill is graded. All right, this one's tricky. Ripple marks. There's two kinds of ripple marks. One represents wavy water. One represents flowing waters. Unidirectional flow, one direction of flow. We call them symmetrical and asymmetrical. Symmetry, even, right? So symmetrical, the peaks are straight up and down. This is caused by wave motion. Water comes in, water comes out, water comes in, water comes out. It all sort of evens out in the end. Asymmetrical, not even. These peaks are pointing in a particular direction. That's caused by one-directional water flow. Downhill, for that matter. So when these get preserved in the rock record, well, we're not at the rock record yet. Yeah, and you see these all the time at the beach. Again, you could even just go up to Lake Ontario and look down, because Lake Ontario is big enough to get some wave action. But at the ocean beaches as well, quit looking at all the people and look down at your feet when you're walking around. You'll see stuff like this. So when this stuff gets preserved in the rock record, you could think tire tracks or giant tank if you wanted to. But if you look around, you'll probably decide that's not the best option. So if you get down and close and look at it, if these peaks are, again, straight up and down, you're in a wave environment, a shoreline environment more than likely. If, however, they're leaning to the left or leaning to the right, you know it was probably a river environment. And if this rock were actually still in its original place, you could tell which way it was downhill back then, because streams flow downhill. Out of context, not very helpful, though. And there's more. Many, many more. Your book might show you a handful. Rain marks can actually get preserved in the rock record. Kind of look like dimples on a golf ball. And there's thises and there's that's. I just pulled a handful. I know for many of you it seems like too much already. That's fine. Again, this is my area of geology. This is what I trained in because I really, really dig it. And so, I get a little more excited about this stuff than some of the others. And that probably comes through, not just in the PowerPoints, but in the conversation. So I apologize if I seem to be favoring this stuff. But surface processes are neat, and they're also much more forward, much more easily understandable than some of the deep physics stuff and everything. Which, again, you know, I have deep respect for those people that study that stuff. But here's my field. So, all right. So this has a chapter in your textbook. I don't know what number it is, but you've got that wonderful table of contents. All right. And I recommend reading up on this. It might be an interlude or two. Okay. And part of a chapter, you'll definitely see it connected with the weathering and erosion stuff. I just, hold on.